Hello everyone. I'm similar to my how to simulate industrial robot using ROS. I'm gonna do a similar series with the mobile base, and while planning this tutorial series, I was searching for different mobile base CAD models in SolidWorks, and from GrabCAD I could find this model which is freely available, and I'll attach the link at the bottom. So it's basically from, I think it's already open, yes. So this model is from Hegu Lee. I hope I'm pronouncing his name right. So you guys can go there and download the model if you want to follow along. And I noticed that this model is basically because it's a differential drive mobile base, so we will have problem due to weight distribution. So there is no caster wheel attached to it. So I also downloaded a free caster wheel from GrabCAD, and it's from this person, Ehan Kosi. I'm pretty sure I'm pronouncing it wrong. So once you have downloaded both of these models, so the mobile robot, you can open the SolidWorks assembly, which is wow, just a moment. So you can download this SolidWorks assembly, which is somewhere here, this one, Carlos. I mean, open the SolidWorks assembly. So when you'll open it, it will basically open this assembly, this whole thing, and then the caster wheel is here. Okay, so in mobile robot, you basically, unlike robotic arm, you have much less links, and there are, like for differential drive, there will be only two moving parts, which is left and right wheel. And the first thing we'll do is basically we'll attach this caster wheel to this SolidWorks assembly, this robot. And if you notice, I'm considering that this is the front part of the robot. So the robot, if you look from the back end, so it will look like this, like it will move in this direction. And I know that like a lot of weight is coming from the front side, so the coming on the back side, I think. So just to balance things out, I'll put a caster wheel in middle here. To do that, you basically to bring the caster wheel in SolidWorks assembly is basically you insert component, click browse, and then use the SolidWorks assembly of download this caster wheel, and then import the SolidWorks assembly into the final, like import this caster wheel into the assembly. And once you have done that, then we need to basically attach this to this one. So you can do that using mates on SolidWorks. So I'll select this face and then click on mate, and then I'll select this face, and they should both be coincident, which means that they'll be connected, and that's one way. And we also know that because it's kind of like a fixed joint, so now I can move it in XY direction, or I mean the faces will always be like that. I'm sorry, I think they should be parallel also, but let's focus about this in a minute. So this face should be aligned with this face, so I can say they are parallel, and then I can change the faces. Okay, so you'll notice that they are actually parallel. Now the problem is, so two things, like please keep in mind two things. One is that I'm not making a real robot, so this is just a simulation, so I'm just making sure that it works in Gazebo. Secondly is that we need to make sure, like I'll make it center, but you'll notice that if it's on the ground, so these two tires should be touching the ground. Sorry, I have the mate selected. So these two tires should be like on plane, on a single plane, on a horizontal plane, which basically is this plane. So to do that, what we can do, I mean, and because it's not a real robot, I can, to be honest, move this part a little up. Let's first make sure that it is centered. So to make it center, what we can do is we can calculate, I want to make this center of this one, so we can check the length from here to here, and this length is about 140 mm, right? And then we can do the same check with for here. We'll measure the length from here to here, and that's about 42 millimeters. So the center point will be at 70, right? And if I subtract 42, half of 42, because this was 140 divided by 2, so the center point, this center line here, will be at 70. And then if I subtract half of 42 from it, which is 21, so this is 49, which means that from here to here the distance should be exactly 49 mm. So one way to make sure that this happens is if I click on mate again. So this is not a SolidWorks tutorial, so I'm not gonna like describe how I'm making the mates, but if you have some so these two lines should be at a distance of 49, I think, right? 49. Please get selected. 49 mm. So this way, so if it is centered, so the other side of it should be at 49 mm also, so we can measure it. Hopefully it will be 49. So I'll rotate this to this point, and the red one is basically the line which is around 49. Yeah. Okay, doesn't need to be exactly at center again, because running simulations I'll probably ignore a lot of things you'll take in account when you're making a real robot. But again, okay, the next thing is that I want to make it so this thing and this thing should be in the same basically on the same plane, on the same line here. So to do that, basically I'll need to move it up, and now again it will extrude this part. So I can hide the battery if you like, we don't need it in the okay, right, it's hidden now. Okay, so let's see if I can move it up. Okay, no, sorry, I had this stupid mate, the first mate, which was and of course the person I think is from South Korea, so all the part names are in Korean, so but that's not a problem. So this is the first mate that I created between the base and this caster wheel. So I'll just remove this and for now, and just see if it moves up. Come on. Remove the second parallel mate also. Okay, so whoa, I've messed it up. see. Free drag, free move. Select the part, click on move, and nope, it's not moving. Perfect. Okay, this is problematic. I'll go into the mates again and delete this mate completely, and yes, okay. Then I'll come back to this and move the cursor, create a mate which is both this face, and please scroll down. My god, I didn't want to keep this video so long, but okay, so it's considering. Please click yes. Okay, so it should not move in the Z direction and in the X direction. Okay, and it should move in the Y direction now. So if I try to, why is it not moving in the Y direction? Oh, so okay, and it can be a distance, and that can be in minus. No, it needs to be in positive, so 0. And can it be rotated? Nope. This is very bad. So, distances needs to be, yes. As you can see, I don't have very good proficiency in SolidWorks. So I'm gonna stop the video and just pause the video and fix this and then come back. Okay, so I didn't want to do everything on like beforehand and then show it on the video, because that's just I don't like such tutorials, because it's fun to see what your thought process is. And I know someone who knows SolidWorks too well, like they'll be laughing at me right now. But what I did is basically I first constrain the rotations by making all the 3 different faces parallel to each other, and then so now it will not rotate. And then what I'll do is I'll make this phase coincident with this one, so this way, not coincident but at a 0 distance, so it will always be here, and then I'll make this face and this face at a distance of 49, which we calculated to be if it is 49 millimeters, so it will be at the center. And the only thing remaining then is basically this z-axis movement, which again it's not doing. Come on, yeah, okay, so it is doing that, but everything else, because there are 5 mates, so in two mechanical bodies can be like one mechanical body has 6 degrees of freedoms, and so if you constrain it in 5 directions, then there is only this one direction that it is moving. And then what we can do is, if I look at it, so you can see that it is almost in the center. We'll also look at value to see, measure it. And now I wanted to have like keep it so that it is exactly at the, it's somewhere here. So I don't want to estimate it. I mean, if I can estimate it right now, but if you're making a real robot, you'll probably put a plane here and then make sure that these 3 tires are touching these 3 wheels are touching the touching that plane in SolidWorks. But one more thing I'll do, because it looks very odd that it is doing this. So we have a mate which is with this one and this one. This mate, and we have it set to a distance of 0. So if I set it to a distance of 5 mm, so it moves forward. So what we'll do is we'll rotate it here, and the final degree of freedom can be constrained by these two, and setting the distance to be, let's say, 17.5 mm. And then if I, let's see it from the sideways, I can move this part, the caster wheel, forward a little bit, which can be done by the first distance measure that I used. So these 3 parallels are basically constraining the caster wheel to rotate in three directions, because there are 6 degrees of freedom in which you can move the caster wheel, I mean the mechanical part itself. And this one is basically constraining it in the positive z direction. So I can edit this feature, which is a mate, and probably set it to 15. So if I move it 15, the caster will move forward towards the left, and I think that looks fine. We can set it a little bit more. Again, please remember that this is not going to be a physical robot, so I can make these changes without having to worry about that how it will be in mechanically. But when you're making a mechanical robot, like actual robot, you'll have to worry about these things. So currently it is basically going from this part is going from inside from this part, which is exactly a collision. Okay, so once we have that, we can save this, which hopefully should work. Okay, so now, as I understand, there will be 4 parts or 4 links. These 4 links will be the left and the right wheel, the base link, which is this whole chassis, and then this caster wheel. So we basically need to define the axis coordinate system and origin on each of them. I just realized, I mean I noticed that recently in SolidWorks exporter you don't need to do that, but I still like to do that. So if you, now we are going to export it into URDF. So you need this URDF exporter, SolidWorks URDF exporter for ROS, and should come up. And once you have set it up, you'll have it under tools. You can Google it how to set it up. So before continuing to solid URDF exporter, we first need to define the origin and coordinate system for it. So we can do this on this face, and because the sub assemblies are not set up properly, there is only one assembly in which everything is inside this one assembly. So we'll have to make use of the sub assembly and put everything in here anyways. So on this face, we'll need the center of this face will be basically the origin of the coordinate system. So I can select the face and then click on geometry and then point, and what it will do is basically it will take the center of the arc, which is this one, and I'll select this face. Oh, okay, sorry, no, center of the face, and then select this face, and the center is basically where the coordinate system and axis of rotation will pass through. Again, because this is the front side of the robot, so this point is basically left origin. I can name it left origin or CS origin, where CS being the center point coordinate system. Is it recording? Okay, so it's still recording, good. Okay, then we can click on reference axis again, axis point axis, and the axis of rotation will be basically coming out of this face, and it's going to be a point and a face and plane. So point is already selected, which is left origin, and the face will be this one. So you can imagine that when the wheel is rotating, so the axis of rotation will be coming perpendicular out of it. So that's one thing, and we'll have to do the same thing for left axis. Just name it properly so that you don't have to worry about other things. So I'll select the left origin again and click on coordinate system. Now, unlike robotic arms, you can select any coordinate system on it as you like in any direction. It doesn't really matter, but I like it when Z axis is moving is outward. So I mean, according to ROS convention, the X should be forward and Z should be upward. So I'll use these faces to make the X forward, so it will be perpendicular to this X, and this is again in Korean because CAD model was designed in Korean language. So okay, so X is here, Y is, which is green axis, is away. I want the X and Y on the plane of the circle. So we can do, so Z should be coming out of this. Oh my god, what am I? So let's see, the Z, if I select Z axis and select this face, so it is coming out of it, and then X and Y can be anyway, because can be in any direction because the wheel is going to continuously rotate. And then I can name it CS, which is coordinate system, or it will be frame for. So this is for the one wheel. We'll have to do the same thing for wheel 2. So I'll pause the video, do the same thing for wheel 2, and then I'll come back. Okay, so I've set up the exact same thing for the right wheel as well as for the left wheel. So if we look from the back side, which is this side, and funnily enough, this might be the first differential drive robot where the caster wheel is on the back side, but this is the right axis, left, and this is the right one, which is this one. Okay, and then we'll set the base link. Base link will be at the bottom, and we can first select this face, click on point, and then here we'll use the ROS convention where the X is moving X is forward, Z is up. So this point will be called it's the origin point, so base link or base origin. I mean, you can name it anything, it doesn't really matter here, but and then because it's a fixed joint, so you won't need an axis here, and then the coordinate system you can select. And for this coordinate system, this is the front direction, which should be X. So you can, there are different ways you can do that. I'll just select this face, so it will always be, orientation will always be according to this one for the x-axis. For the y, for the positive y, it should be in this direction, and for z it should be upward. So there is this axis which is pointing the positive, the forward direction is positive x-axis. So you can name it, let's say base CS. Okay, so a few moments ago I said that there might be 4 links, there may be 4 links, but we'll set it up for 3 links, where we have left, right link, and right wheel link, left wheel link, and then base link. We'll not include the caster, and we'll include the caster into the base link. So once you have this done, you can I'll save it first, and once it is saved, then we can open the URDF exporter tool. So I'll go to my tools under SolidWorks, and then scroll down, and this is export as URDF option. So I'll click here. It will ask to remake the assembly first, and then it will open this. Perfect. So here it is, the first option is base link. Like it might be something else, but you can name it base link, which is the root link of your robot. It's asking for the global coordinate system, so I'll select base link here, and then in here we need to select all the parts, all the parts which belongs to the base link. So what we can do is we can select everything, and then one of what was not selected, it should be everything. Part is not, where is this part? Oh, okay, sorry, it's on the top. okay, sorry. So I'll go again here and click on export URDF. Base link, it should be base link, and then this goes here, right? So from here we'll select everything until caster. So, and then we need to deselect it, so I'm holding down control key and then unselect wheel 1 and wheel 2, and the center point is deselected, and then tire 1 and tire 2. So these are not part, these black part and wheels are not part of base link. And then in here I'll select, there are 2 links, so like there are 2 childs of this base link, one will be left joint and one will be right joint. So it will be joint, this should be link left, joint, I'll name it joint left. The reference coordinate system will be left coordinate system, reference axis will be left axis. The joint type will be continuous because it's a mobile base, so it will not have joint limits, position joint limits. And then for the link I'll select, so it needs to be left link. If you see here, this is the right one, this is the left one, so you need to select this, and then this, oh no, sorry, this one. So this part is link 1, it has no child, so we can select this one and then click on empty link. In the empty link it will be link right joint, the name of that the name of that joint which connects link right to base link will be joint right. Reference coordinate system will be right, and then the reference axis will be right axis. Joint type will be continuous, and then here it will be this and this. Come on, select this. Okay, so selected it. Okay, so this will be the right joint. You can see because this is the forward direction, so this should be the right link. And once it is selected, you can click on preview and export. Okay, once you have this window open in preview SolidWorks assembly to URDF exporter, you can select joint left from this end, and then it should autofill these types. Just make sure that this is continuous. I think I did not select it there. So joint type should be continuous from mobile base because it will continuously rotate in velocity mode or speed mode. Continuous coordinate system is correct. These are autofilled orientation, so we don't need that. And again, because it's a continue. Come on. There will not be any lower and upper limits on the joint position because again it will continuously rotate, but there will be limits on the effort, which in this case will be motor torque. So I'll just randomly select 2, which is 2 Newton meter, and velocity will be, let's say, 0.5 meters per second, or radians per second, sorry, which I think is a little low. Let's select 0.5. We can change it later on in the URDF. We don't need to select your calibration or dynamics. I mean, if you want, you can add these, and then in Gazebo it has an effect, but I'll just not add any value here. Here also it's continuous, joint right type is correct. Here we'll select the same torque value and same speed. I mean, hopefully you connected the same motors for the left and the right joint. And then there is this mimic, and I keep clicking outside of this. There is this mimic other joint, and this is used when you have 2-finger robotic gripper, because in 2-finger robotic gripper, or even sometimes in 3-finger robotic gripper, only one motor is used, so that like the 2 links are basically, one of the link is mimicking the other one using special gear arrangement. So it's two in URDF, that's how you define it, using mimic other joint, but we're not making grippers, so let's forget about it. And then click next, and then we have this inertia and other properties. If I select base link, and it should be auto filled, hopefully. Okay, yes, so my computer is like working a little slow, but based on the material that you assign in the SolidWorks, which it was already assigned when I downloaded the CAD model, so it calculates the mass based on the material properties and material density and the amount of volume in the CAD. And you can later on change it in the URDF if you want. I mean, I'm not going to. So in total, if you look at it, the mass of the wheel is about 0.1 kg, which is 100 grams, and the mass of the base is about 0.6, I think, which is 600 grams. So in total it's about a 1 kg robot, like 0.9 kg. It's 0.9 kg heavy robot. And then here in the mesh details we'll select fine, and we don't have any material name or everything, so these are related to how the robot looks. I'll just select it so it looks nicer in the robot, in the Gazebo, and then I'll click on export URDF and meshes. And once we have it here, we can go to, I'll go to my desktop. No, not here, mobile base. Okay, so I already had a tutorial set up. I'll just change this name. I recorded a tutorial and then back up. So I thought about the name of this package, so we'll just name it YouTube base ROS. And here this will be the name of the package. So YouTube YT base ROS will be the meta package, and within that there will be different ROS packages related to this robot. So the first one will be UT base and description. Normally it's not a convention, but like people use underscore description as the for the package name, which includes all the URDF. And then it creates this. So this is the first part of how to simulate a mobile base in robotic mobile base in ROS 1, and we'll use Neotic. In the next tutorial we'll go ahead and make some changes in these exported URDF files. So if I show you, I'll go to the mobile base, YT base. So it will create this YT base description package. I'll open it, and in the hopefully this text is big enough for you to see. Okay, so it automatically generates this config. Like there are different folders. We don't need this joint names folder. We may need these automatically generated launch files, and then the meshes are here, and then textures we don't need. We actually didn't define it. And then YT description, this part we might not need, and then this part is what is the URDF. We'll make changes in this URDF in the next tutorial to include the Gazebo ROS control support. And so the next tutorial will be about how to include Gazebo ROS support in this. Move the robot in velocity mode using hardware interface velocity controller. And then we'll include in the third one we'll have move base with local planners. And then we'll include some because there are no sensors on it right now. As I see it, there are no sensors, so we'll probably add real sense camera and LiDAR camera, simulate those in the fourth one. So and then add try to do SLAM on it. So there might be 4 to 5 videos in this tutorial. So let's see how it goes. So see you in next video. If you can, please subscribe to the channel so I can get motivation to record more of these videos. Thank you. Bye.